Hello, Miss. My name is Esteban Moyano, and my group is made up of Sheila Winesa and Imo Bravo. Our general objective is determine the convection mass transfer coefficient on a flat plate by analyzing the moisture of our coffee samples to predict the behavior of fixed second level in conversion process. And a specific objective, we have compared the moisture of coffee samples through the estimations of the dry solid mass and the amount of water after drying in process. And finally, the variations of misery of over time in different coffee samples by constructing the dryer curves. In materials and equipment, we use it in substance as coffee husk, distilled water. In materials to crucibles, spatula, tweezers, pisetta, and in equipment, we use analytical balance, desiccator, and dryer. In procedure, previously, dry crucible for 2 hours was weighed in 2 grams of coffee beans were weighed in the crucibles. The crucible with the sample was placed in the overhead at temperature of 120 degrees Celsius for 5 minutes. After 5 minutes, the crucible with the samples was removed and placed in the desiccator for 10 minutes. The crucibles with the samples was weighted on the balance, also the cycles was repeated for until for mass date. And finally, worked and duplicated, obtaining the following values.
Hi, my name is Ivonne Bravo, and I'm going to talk about the experiment data. As my partner Esteban Moyano was talking about the procediment, we obtained this data with the procediment that we realized previously. First, we have the crucible mass that was 85.9711. How do we obtain the results? I'm going to talk about with the equations that we use. Then, with the second experiment, we obtain a crucible mass of 86.50. Now, what are the equations that we use? We use equations for the determination of the diffusion coefficient of water. First, we have to know what was the dry basis moisture and was a division of we can see here in the slide. Then we calculate the moisture ratio, and then we calculate the weight basis moisture, and finally we calculate the total mass. And what is the total mass? The initial water mass plus the dry solid mass. Then we calculate the diffusion coefficient of water with this equation of natural logarithmic, with this equation that is very extensive. The most frequently used dimensionless correlations are divided into 3 groups, of which we will use the Sherwood number, including the mass transfer coefficient, Smith and Lewis number required for 2 simultaneously use different transport processes, and the Reynolds number used to describe the flow type. Simultaneously, using the second law of Fick diffusion with considerations such as a flat plane, isothermal drying, constant effective diffusivity, and negatively contraction and external resistance, we arrive at the expression of the diffusion coefficient of water that were shown in this slide. Okay, taking into account that the slope of time versus the logarithmic natural of the moisture ratio, is this helps us directly calculate the diffusion coefficient of water. As I was mentioned, we obtain this correlation with the natural logarithmic moisture ratio versus time. Now I'm going to explain, this was of the duplicate of the experiment, and now I'm going to explain our results. In the laboratory, 2 experiments were conducted with coffee pulp to perform a parametric study using data obtained for dry basis masses. In other words, obtaining the natural logarithmic moisture ratio, where this moisture ratio is the dependent variable and time is the independent variable. These graphs yield equation of line with negative slopes that help us to calculate the diffusion coefficient of water. Using the previously presented formula, the result was this: 1.277 divided by 10 to the power of 9. And for the other trial, the result was 5.066 divided by 10 to the power of 9 meters quadratic plus divided to seconds for each respective experiment. Subsequently, as the calculation of the mass and heat transfer coefficients required dimensional numbers that I was mentioned previously, an external tool was used to calculate gas properties. What we use the EES program that helped us to calculate the specific heat, the thermal conductivity, density, and dynamic viscosity values of the gas at ambient temperature and pressure that we obtain. Additionally, under the same condition, it was found that Reynolds number indicates a laminar flow for both experiments. Obtaining these values, the mass transfer coefficient was determined to be 1.389 divided by 10 to the power of 4 and 1.267 divided by 10 to the power of 5 meters divided on seconds, while the heat transfer coefficient were found to be 10.96 and 0.40 watts per square meter per Kelvin for each respective experiment. In general, if the mass transfer coefficient is very slow, it will decrease. It implies that the convective mass transfer between the surface and the fluid is definite or limited. Conversely, if the heat transfer coefficient is high, as in experiment 1, it means that the convective heat transfer between the surface and the fluid is efficient and rapid. Thank you.
Hi, I am Sheila Vinuesa, and I am going to talk about the discussion. So as you know, coffee is probably one of the most popular beverages in the whole world. This product is the second largest traded commodity, surpassed only by the petroleum. In the soluble coffee industry, spent coffee grounds present moisture contains between 85 and 90%, talking about wet basis. Models of thin layer drying that describe characteristics of biological material consist of 3 principal equations. First, we have the theoretical equation. Second, the semi-theoretical equation, and finally, the empirical equation. So the 2 first equations are really hard to use. On the other hand, the empirical equation is the easiest one to calculate. So we have a plus. This model is widely used. That's the principal reason why we chose this equation, with the experiment drying data to identify a suitable equation for describing and predicting the drying behavior of this product. Now we have the conclusions. In our experiment, 2 trials were conducted involving the drying of coffee husk using a forced convection mass transfer process. Basically, in this process, a hot air flow was applied to the sample to extract the water contained in the coffee husk. The remaining mass of the coffee husk in the crucible was recorded approximately every 5 minutes, as we showed before. With this information, we made the graphics, initially obtaining the water diffusion coefficient using dimensionless numbers such as Sherwood, Reynolds, and Lewis. The mass transfer coefficient for this process was determined. The results were 2. The first one was 1.381 times 10 to the negative 4 meters per seconds, and the second one was 1.267 times 10 to the negative 5 meters per second for the second trial, obviously. These values are quite close considering that difference in the weight of the crucibles used. So that's all. Thank you.